Graphene may be considered the simplest from all nano-objects, but the beauty of this elementary structure hides important fundamental challenges. In fact, the atomic thickness nature of graphene defies the classical model of material mechanics. This video tells you about these challenges and ways to circumvent them. We will concentrate particularly on the elastic properties of graphene and consider two different approaches to tackle the problem. The first method will consist on start from the elastic properties of graphite, the 3D structure obtained by stacking graphene layers, and remove one dimension. In the second technique, we will again consider graphite, but this time we will make it as thin as possible. In the first approach, we consider Hooke's law in its tensorial version as shown here. We have then, for an hexagonal crystal, an elasticity tensor having only 4 independent constants. We are then going to remove the Z component outside of the graphitic plane. This is component number 3. In Voigt notation, this means that we make 0, all components having alpha 3, 4, or 5. We are then left with only those components of the elasticity tensor having alpha indexes 1, 2, or 6. This leads to the following simplification of our tensorial elasticity expression. In an hexagonal system, in addition, it is possible to show that the obtained tensor is invariant by in-plane rotations, and this is done using symmetry arguments. This means that the in-plane elastic response of graphene should be isotropic. The reduction from 3D to 2 dimensions of the elasticity tensor left us with only 2 independent elastic constants, namely C11 and C22, as we have seen in the previous slide. These 2 elastic constants have made the object of different measurements. This table shows the best experimental results from 2 different works. But the question that we have the right to ask is, are these constants preserved after having reduced the dimensionality from 3 to 2? We should think about what represents the elastic tensor, and its definition includes a relation between stress and strain. Stress is a force per unit area, but what is the lateral area of an atomic thin plane? If we could define such area by giving to the graphene plane a thickness, let's say h, then we could introduce a relationship between 3D and 2D stress and elastic constants. The key element is then the introduction in some way of an arbitrary value of such thickness. We now consider a second approach to study the mechanical response of graphene. This time, we are going to consider graphite again and apply the so-called Kirchhoff law theory, which is a model for the elasticity of very thin plates of material. We are not going to describe this model into details, but just explore its consequences and possible limitations if we apply it to the study of graphene. One of the uses of this KLT approach that can be very useful is the exploration of the vibrational properties of membranes. Look at these modes. These are the 3 first modes of a circular membrane. The first one, we see that represents just the membrane moving up and down. In the second one, we observe a mode that represents a kind of a Mexican hat shape. And the third mode is let's say, asymmetric version of the Mexican hat. Within the KLT model, we can define a number of very important variables to describe the elasticity of the membrane. The first one is the extensional stiffness of the plate that we are going to describe in the next slide. The most familiar for us will be the 2D version of the Young modulus, that is the so-called in-plane stiffness constant. You see that both A and C are given in newtons per meter. That means that we have removed one of the dimensionals with the length dimensions with respect to gigapascal. Another important variable is the bending stiffness or flexural rigidity. That is going to be a measure on how easy is going to be to bend a membrane. Then we have the in-plane Poisson coefficient with its usual definition, and another Poisson coefficient which in principle should have the same value that the previous one, but which appears in the bending calculation. We call it nu prime. Finally, we can consider G the in-plane shear stiffness. The extensional stiffness is just the proportional constant between the strain components and the so-called tension components, which are just the 2D analogs of the stress components. Of course, the number of tension components will be of 3 and can be then shown to be related to the strain components through the following relationships. As we have already shown from the previous approach to the elasticity of graphene, we expect to have only 2 independent elastic constants to describe graphene elasticity. We have then different relationships relating the previous defined variables in order to finally get the 2 independent elastic constants. Again, we find that the defining H, the thickness of graphene, is the K element of all these models. In the case of graphene, we may expect in addition that nu and nu prime, the last one being related to the bending equations, do not have the same values. The reason is that extension is controlled by sigma bonds, whereas bending derives from pi orbitals. As a final consequence, we may expect that for high bending, leading then to changes in the balance between pi and sigma bonding interactions, the elastic constants themselves can be modified. So we have already underlined this several times in this video. A K element to study graphene elasticity is the value of its thickness. The thickness can be, for instance, imagined as determined by the dimension of the nuclei of the carbon atoms or by the extension of the electronic orbitals. In fact, many different calculations, as shown in this table, give thickness which can differ from each other even up to 1 order of magnitude. So to compute the thickness, expression as this one, making a relationship between the elastic constant, here the bending stiffness, and the in-plane stiffness can be used. These elastic constants are calculated by models using the carbon interatomic potentials, and these elastic constants are derived as derivatives of the carbon interatomic potential. These interatomic potentials differ from one model to the other, and this explains the difference of values. So to put some order in all this, the scientific community is making the choice of adopting an arbitrary value for the thickness of the graphene plane. And this is taken as the intergraphene distance in graphite, and its value is 0.335 nanometers. When reading papers then or reports, you should then look for the use value for that thickness to be able to compare one work to the other.